they have partially got the genome out of it, and the genome shows that the DNA in it is in much bigger chunks than it is in modern humans. So the DNA is in larger pieces from Neanderthals. It's much closer to the time of interbreeding 45,000 years ago. So what they did was actually to look at the genome in modern humans and how much it's broken up, compare it with the DNA in this femur from 45,000 years ago, and they were able to calculate, remarkably, that the interbreeding happened about 330 generations earlier than this owner of the femur was around. So that puts it about 10,000 years earlier than 45,000 years. So the interbreeding is constrained, it seems pretty accurately, to 50 to 60,000 years ago. So remarkable. But there's no greater amount, it seems, of DNA in this femur from Neanderthal than we have today. So the Neanderthal level has shrunk down a bit, and we'll come to that in a moment. Then, and I was asked to talk about this, but it gets very complicated, there's another lot of people called the Denisovans that we've learnt about from DNA studies. So a cave in Siberia, called Denisova Cave, had some really fragmentary fossils. A couple of teeth, very big teeth, and the end of the femur bone. Not enough that you could possibly say what species this was, except the teeth were so big it didn't look like a modern human. But from the end of the finger bone, the DNA in that little bone is as well preserved as a modern human bone, and it's produced a complete genome, this tiny little finger bone. And these people were distinct from Neanderthals, distinct from modern humans, so they've become known as the Denisovans, known from this site. And the remarkable thing was, when the DNA comparisons were done with modern human genomes, there was only one region of the world that showed any greater resemblance to the Denisovan DNA. And rather surprisingly, that was down in New Guinea and Australia. So remarkably, we don't think the ancestors of Australian Aborigines and New Guineans ever went anywhere near Siberia. They came from Africa through southern Asia, down Southeast Asia to New Guinea and Australia by boats, almost certainly. So the likelihood is that Denisovans not only lived up here, but they must have lived down here as well. That's where the interbreeding happened, and that was taken on into Australia and New Guinea. And this is something I published a couple of years ago in Nature, but it's a little bit out of date now because the figures of interbreeding have been revised. But we can say that Eurasians and Native Americans have about 2% Neanderthal DNA. People in Australia and New Guinea have about 2% of Neanderthal DNA, and I think the figure now is about 4% of Denisovan DNA as well. So they've kind of got a double dose of this interbreeding. And even in Africa, there's evidence from an unknown source of archaic DNA going into sub-Saharan Africans. And that's why I think we should remember that 50% of Africa, we don't know who was living there, was there an archaic lineage surviving in Africa that interbred with African populations. Okay, so that's my interpretation of how to explain things. So we've really concentrated on this story. So Heidelbergensis didn't just give rise to modern humans in Africa and Neanderthals in Western Eurasia, it probably gave rise to Denisovans as well, and there was a bit of DNA picked up in interbreeding, and even a little bit continuing from archaics through to modern humans. So I really do have to draw to a close. I would say now, in terms of where the recent African origin model is, that it's certainly not 100% recent African origin, which some people were prepared to say a few years back. We are certainly more than 90% recent African origin in terms of our DNA. I would argue probably in our behaviour as well, and our morphology, but not entirely so. So recent African origin and hybridisation is the model we should be talking about. You could call that maybe mostly out of Africa. Svante Pääbo's term is leaky replacement. So yes, there was replacement of these other types, but there was a bit of interbreeding. So that's where we are, and we really probably are talking about situations similar to baboons in Africa. They look like they're good species, they have different behaviour, different morphology, different coats, different diets, but when you look at their DNA, they're doing a little bit of interbreeding. Lots more data on Neanderthals, which I can't talk about now, but evidence that in our genomes there is some association of certain diseases with the presence of Neanderthal DNA in certain clusters, including, as it says here, type 2 diabetes, Crohn's disease, lupus, biliary cirrhosis, and even the inability to give up smoking. Any of you got that problem? And we know that Neanderthals had very small population sizes, and they were very invariant, and they were even inbred. The best complete Neanderthal genome from Siberia suggests that that girl was the product of interbreeding between either two half-siblings, an uncle and a niece, an aunt and a nephew. That level of interbreeding was going on. So I think we've seen how much the climate's affecting things, and I think that's what's hitting Neanderthal diversity and the Denisovans as well. We've only got one Denisovan genome to high quality, but it too shows very low variation compared with modern humans. So I think they were endangered species even before modern humans came out of Africa 60,000 years ago. I won't talk about that, but I will just mention our exhibition. Last plug for that. Some of you may have a poster that's outside for the exhibition, but in there we have got a discussion of the interbreeding, and we've got this great model of a Neanderthal done by the Chemist brothers, which is great viewing. There he is. So do come to that exhibition if you can. It's there till the end of September. Right, I'll stop there. Thank you.